So we're talking about many, many generations of people who will have to live with these high carbon dioxide concentrations unless we manage to, cut emissions soon and reduce emissions, eliminate them altogether, but then also possibly sequester carbon dioxide that has already been emitted from the atmosphere and store it somewhere in a stable reservoir.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective on important societal issues.
Produced by Soapbox Media.
The world needs evidence-based public policy now more than ever. Making the right decisions should not be partisan politics. Please help spread The Rational View by going to patron.podbean.com/The Rational View. Together, we can make a better future. Hello and welcome to another episode of The Rational View. In this episode, I'm returning to a topic that's become, a favorite for pundits and trolls, and that is carbon dioxide. The near doubling of the atmospheric concentration of this colorless, odorless gas has been identified by scientists as contributing to an accelerating heating of the biosphere that has significantly affected global climate. As a byproduct of one of our most lucrative industries, however, the burning of fossil fuels, CO2 has also gained a lot of friends, and because of that, it is the subject of a targeted disinformation campaign, becoming headline political news around the world. This is obviously a job for The Rational View. If you like what you're hearing, I hope you press like on your podcast app, share the love. Come chat with me on my Facebook group. If you have any questions, I'd love to talk to you. I'd love to hear from you, and support the podcast. Thank you so much for listening. Bärbel Hönisch grew up in Germany and studied at the universities of Bielefeld and Bremen, as well as the Alfred-Wegener-Institute for Polar and Marine Research in Bremerhaven. She received her diploma in biology in 1999 and her PhD in natural sciences in 2002. After moving to the U.S., she held academic positions at the Lamont-Doherty Earth Observatory of Columbia University, the City University of New York at Queens College, the State University of New York in Stony Brook, and Bremen University. She joined the faculty of the Department of Earth and Environmental Sciences at Columbia University in 2007. She's interested in the effect of global carbon cycle perturbations on climate and the oceans. In particular, past variations of seawater acidity and its relation to atmospheric CO2. As she was originally trained as a marine biologist, her research includes culture experiments with living marine calcifiers to validate proxies for past environmental conditions. She applies the resulting calibrations to reconstructing seawater carbonate chemistry and atmospheric CO2 variations through Earth history. Over the past 7 years, she's led a consortium of paleo-CO2 proxy experts to compile, vet, and modernize published paleo-CO2 estimates over the Cenozoic. Dr. Hönisch, welcome to The Rational View.
Thank you very much for having me.
So on this podcast, I kind of try to dig down to the evidence behind polarized issues, and there are few issues that are more polarized than carbon dioxide in the atmosphere. Here in Canada, the carbon tax is becoming a wedge issue in our next election. What got you interested in CO2 and leading this group? How did you come to be in this position?
That's a very good question. So carbon dioxide is certainly something that is particularly interesting, and it has been very polarized even in the research community. So this is one of the reasons why we actually worked on this consortium over the last 7 years to bring people together and to make sure that we actually all showing the same results in a collegial way. So as you already indicated, I started out as a marine biologist or a biological oceanographer. And when it came for me to defend my thesis and then to think about what I'm going to do in the future, I thought it would be more interesting to work on something that has global appeal or a global interest, in particular for taxpayers, than to work on particularly local questions. And when I was a graduate student, I worked in the carbon group of the Alfred-Wegener-Institute for Polar and Marine Research in Bremerhaven.
Mm-hmm.
And that was a group that was particularly interested in what is happening right now, what happened in the past, and how can we model this to make better predictions for the future. And since I came from the biological oceanography side, I was particularly drawn to the work of my then thesis advisor, who cultured planktic foraminifera and tested these different proxies in different environments.
So this is your bio on culture experiments with living marine calcifiers.
Exactly.
Yeah, it's not taking them to the opera; it's actually culturing.
we actually culture them in the lab, and I specifically work on planktic foraminifera, and those are organisms that look like little popcorn. They're really about this big, the size of the pin of a head, head of a pin. Okay. And they're very, very small, and they secrete calcium carbonate shells like snails as they're living in the ocean. Okay. And when they're doing that, they incorporate the chemistry of the water into their shells, and in some cases also the physical conditions of the environment they're living in. And they live for about 4 weeks or so, and when they die, they sink to the bottom of the ocean. They litter the seafloor. We can take sediment cores out of the ocean, and we get layers, timed layers. So the youngest sediments are on top. The deeper we go, the older it gets. So we can get time series out of the seafloor. And we can then analyze those shells and reconstruct the climate at the time when they were living. And so as a graduate student, I was mostly interested in learning about them in the first place, culturing them, understanding how they actually record the environment. And then later on, as a postdoc, I came to New York and I started working on the paleo reconstruction. So I started working on sediment cores. In particular, in the beginning, I worked on the last 450,000 years. Over which time, at the time, we had ice core measurements of carbon dioxide in the atmosphere. And so I could directly compare my reconstructions to the ice core measurements. It's sort of the ice core measurements are sort of the gold standard of carbon dioxide.
So let's just back up and make sure we understand. So you have ice cores. So people have drilled down through glaciers to get actual measurements of bubbles of carbon dioxide from ancient atmospheric conditions. Is that correct?
That is correct.
And how far back does that record go?
So right now we have records back to 800,000 years ago. There are a couple of snapshots that go back, I think 2.5 million years ago. They're just small little pockets of ice that have been investigated. And right now there's actually a suite of various different drilling expeditions happening in Antarctica from various different nations, from the US, from Europe, from I believe Japan, and maybe even Russia. I'm not so firm on that. But there are several expeditions happening right now where they're trying to drill further back in time and to collect ice that may be as old as 1.5 million years in a continuous record.
So that ice has been there undisturbed or growing for over 1 million years, is what you're saying?
Yes.
Wow. And so you sample these cores and you get truth for what the atmosphere really was by measuring bubbles of air in the ice cores. And now you're comparing them to what exactly?
So I'm not actually the one who's measuring the bubbles in the ice cores. That's done by experts in labs that actually have the facilities for that. But I compare my data to that. So I'm working on these planktic foraminifera, and I take them from sediment cores. And so in the sediment cores, we also have a timeline. So we take them out of the sediment, we analyze them, and then we compare the chemistry of these organisms, of these fossil shells, to the calibrations that we have established in the laboratory in culture.
So you're growing these in different conditions or different levels of carbon dioxide and different levels of carbonate dissolved in the water, different pHs and that sort of thing, and figuring out how that affects the carbonate in the shells. Is that correct?
Exactly. So the specific proxy that I'm working on is the boron isotope proxy. And that is a proxy that actually reflects seawater acidity or seawater pH, as you already mentioned. And the seawater acidity is in direct relationship to the carbon dioxide in the atmosphere. So the higher the carbon dioxide, the more acidic the seawater is. The lower the carbon dioxide in the atmosphere, the higher the pH of the ocean is, the lower the acidity of the seawater is. And so by measuring the pH, we can then infer what the carbon dioxide conditions were at the time when these organisms were living.
And how do you get the correlation to years? Like you're digging a core of sediment out of the sea floor, I assume. how do you know which year corresponds to how deep in that sediment?
So first of all, we don't get years. We wish we could get that. So that's the beauty of the ice cores. The ice cores are really annual cycles, sometimes even subseasonal cycles. The further back in time you go, the more that gets compacted and the harder it gets to get the individual years. But in the sediment, we really work on 1,000-year time scale. So for a typical sediment core that we would take that is somewhere on the order of 2,000, 3,000 meters water depth, those are places where the sedimentation rate is on the order of 1 to 2 centimeters per 1,000 years. So we get about this much material per 1,000 years. And then the organisms at the bottom of the ocean who actually dig through the sediment. And so they mix up this entire signal. So we wish we had a much higher resolution, but we cannot get that from the geological record. And so, but that still doesn't take away your question. So we still need to find out how old was that sediment. And there are various different ways of doing that. Back to 50,000 years ago, we can take radiocarbon. So we can actually measure the radioactive carbon that is in these fossil shells. But that only brings us back to 50,000 years. And we really want to go back to hundreds of thousands and millions of years. And so for that, there are various different ways of how scientists are doing that. In some ways, we can look at the magnetic striping in the sediment. So we can look at magnetic reversals of the Earth magnetic field, and so those have been timed. So they have been the age of those reversals has been estimated based on geological analyses. And so if we find those in the sediment, then we have an indication for how old individual spots in the sediment are.
So you can measure the magnetic field in slices of your cores.
Yes.
In what, like iron particles in there, or is?
So there are various different particles in the sediment. There's magnetite. There are all kinds of other particles in there that actually orient themselves as they're falling to the seafloor based on the Earth magnetic field. And so that can be analyzed in these cores. And then on top of that, we probably the most widely used way of doing this is to work on oxygen isotopes. So every single one of these calcium carbonate shells is made out of calcium, carbon, and oxygen. Mm-hmm. And the isotopes are various different flavors of the individual elements. So they come in different weights, and depending on how heavy they are, they respond slightly different as they're being incorporated. And we know from our analyses that we've done that during ice ages, the isotopic composition is much heavier. So we have more oxygen 18 in the samples and less oxygen 16. And that also correlates with temperature. And so there are these beautiful cycles when you're going back through time that actually correlate with orbital cycles. So orbital cycles mean how does the Earth actually circulate around the sun? How close is it to the sun? How far away is it? Which way does the northern hemisphere lean during the northern hemisphere summer? And so that is eventually the cause of our ice ages. And so we can see these beautiful cycles directly in these oxygen isotopic compositions, which are easy to measure, and we can measure them in very high resolution. And so we see these beautiful cycles. We can compare them to assessments of the orbital cycles in outer space. And so that gives us a sense to estimate what the time was in the past.
Interesting. So you're measuring these oxygen isotopes in the shell, in the compacted shells, basically on the seafloor. So how far back does this seafloor record go? So
these planktic foraminifera that I'm working on, that is actually the basis of a lot of paleoceanographic research right now, and they have been dominating the oceans for about 100 million years.
100 million years! Wow.
I have done reconstructions that go back to 56 million years, and so that was mostly also the time interval of the study that we just did. We went back to 65 million years, These organisms or the sediments, they get more and more compact the deeper you go. As you can imagine, if you have hundreds of meters of sediment, they get really.
So you're losing resolution in age as you go
you're
deeper.
Losing resolution, and they really turn into rock. So that makes it very hard to break that apart and then to isolate individual specimens, and in particular the ones that belong to a single species. And that is important for us to do as well. We cannot mix random species because they lived in slightly different environments, and then that falsifies our analyses. So we have to be very careful with that. There are studies that have been done over these very long time intervals, but they're very sparse so far. We've really only started going this far back in time for the last 10 or 20 years or so, and so there are not very many studies that have been completed for
so you can recognize which species these shells are coming from, and you use that to get a more robust measurement of the CO2 proxy. Is that correct?
Exactly. So I am specifically interested in species that lived very close to the sea surface, because if they live deeper in the ocean, we have all kinds of other organisms that eat organic matter, that eat plankton that's sinking down from the sea surface, that releases carbon dioxide in the water. And so we don't want that to falsify our measurement from the sea surface. So sea surface in many places is exchanging, or the sea surface is exchanging carbon dioxide everywhere in the ocean. But there's some places where it's actually in equilibrium with the atmosphere. That means that the carbon dioxide concentration is the same in the atmosphere as it is in the surface ocean. And those are the places where we want to do our reconstructions.
I see. So your group has published a paper. Your group is called CO2 PIP. Is it Cenozoic CO2 Proxy
Integration Project.
So you've gone back and estimated the atmospheric CO2 level up to 66 million years ago. Is that correct?
Yes, we didn't actually estimate that ourselves. We actually used published information and looked at these records and tried to find out which of them are still reliable, which ones are actually conforming to our modern understanding of how these proxies are working, and which ones may not be reliable anymore based on the new information that we have learned over time.
Okay. So how many proxies are you looking at when you're putting this all together?
So we have now looked at 8 different proxy groups. Some of them are terrestrial, some of them are marine. All of them have been tested in one way or the other, in particular against modern times. Ideally against the ice core measurements, because the ice cores are sort of our gold standard for what carbon dioxide was in the past. And if we can reconstruct that, then we have greater confidence in the in past variations.
Right. And so how well do each of these proxies track each other over this period? Are you relying on just one proxy for most of this period, or are there multiple proxies that are saying the same thing?
We're trying not to rely on single proxies, because the further back in time we go, we actually work with different organisms. So the modern species that we're working with right now, they only evolved over the last couple millions of years. And if we go back 30, 40, 50 million years ago, then those species that existed then do not exist anymore now. They went extinct in between. So we have to be very careful and very mindful of all of these different changes that have happened over time. We also need to be concerned about the elemental and isotopic composition of the seawater and the atmosphere, which have also changed through time. And so all of those are parameters that become more and more uncertain the further back in time we go. And that is the reason why we're particularly interested in comparing our results from various different proxies. And so if we get the same answer from all the different proxies, then we can be more confident that what we're estimating is actually correct.
What are some of these other proxies that you're using?
So I'm just using the boron isotope proxy, but in this consortium, we have experts that work on terrestrial proxies and that work on marine proxies. On the marine side, we also have phytoplankton, and the phytoplankton, as they photosynthesize, they take up carbon dioxide, and depending on how much carbon dioxide there is in seawater, they take up more or less of a stable isotope, carbon-13. Carbon-12 is the most abundant isotope, and ideally, the phytoplankton would prefer that carbon-12 because it reacts much faster. It's the lighter isotope. But when carbon dioxide becomes more limiting, they will also take more of this heavier carbon-13 isotope. And so by looking at the isotopic composition of the carbon isotopes in organic substances that these organisms produce, we can actually reconstruct the carbon dioxide in the atmosphere. Or my colleagues can do that. I'm not an expert in that. Then we have several different terrestrial proxies. The easiest one to understand is probably the leaf stomata proxy.
Okay.
And that is an indication for how much carbon dioxide there is in the atmosphere based on how many breathing cells leaves have. So stomata are called breathing cells. They're the cells in the leaf that allow leaves to take up carbon dioxide from the atmosphere. But leaves have to kind of balance how many of these cells they have, because when they open them, then do not only take in carbon dioxide, but they also lose moisture. And so a tree wants to keep that moisture, but it also wants the carbon dioxide. And so the more carbon dioxide there's in the atmosphere, they can afford having fewer of these breathing cells. And if they have fewer of those breathing cells, they lose less moisture. So there's sort of a delicate balance for the trees that they want to maintain. And so there are various different ways of measuring that. And we have other much more, and that's one of the easier proxies to understand and to work with. But the more sophisticated ones that also specifically look into the geometry of the leaf and how it takes up carbon dioxide and how it actually moves around in the leaf and also benefits from isotopes. Then there are proxies that look into soils of minerals that precipitate in soils depending on how much carbon dioxide there is in the soils, which again is in exchange with the atmosphere. So there are some changes on that front. And then there are minerals that precipitate over time in certain environments. And those minerals precipitate depending on how high or how low the carbon dioxide is. And if it's higher than a certain level, then you get the one kind of mineral. If it's lower than a certain level, then you get the other kind of mineral. And so some of these proxies, you can already tell that are not giving us the absolute number. They just give us relative numbers to one or another point of reference. But they're all very, very helpful for us to evaluate all our different proxies and to validate these data that we collect through time.
Are there any proxies that are giving you wildly different results, or are they all basically quite similar and you're just kind of trying to find the absolute level of them?
There are differences in our reconstructions. In particular, if we're looking back at the time sort of between 35 and 20 million years ago, the marine proxies give us somewhat descending carbon dioxide values, and some of the terrestrial proxies do not. They give us flat values over that time. And that's a very, very interesting time interval because the temperatures did not actually change over that time very much. And so now the question is, are proxies wrong? Which of the proxies is wrong? Do we not understand the relationship between carbon dioxide and temperature? Is there something else in the climate system that is affecting this? Or are our temperature proxies wrong? So all of these are potential complications that we need to deal with. Over and over of this, overall in this record, we have seen a very, very close relationship between what our temperature proxies are indicating, how warm it was, and when it became cooler, the carbon dioxide levels were decreasing. The carbon dioxide levels were much higher when it was much, much warmer. And so overall, that works very, very well together. But there is this time interval that is sort of a little bit enigmatic. So we've known that for a long time. We've probed into it, but we still need to do more research to try and find out which of these data are actually correct, and whether there's something in our climate system that we do not understand.
Are you retrieving carbon dioxide and temperature and climate information from your proxies?
So in particular from our planktic foraminifera, we can actually measure both. We can measure the carbon dioxide and we can measure the temperature. We need to use a different proxy for that. In most cases, we're now using the magnesium-calcium proxy, which is a temperature indicator. We are also using oxygen isotopes. They also relate to temperature, but they also relate to ice volume on our planet. So we need to back that out, how much ice was on the continents and not in the ocean. So that has an effect on that. So there are lots of different parameters that we have to pull together in order to come up with an estimate of atmospheric carbon dioxide.
I see. And how accurate are your reconstructions? How many parts per million can you confidently ascribe to different periods?
So that really depends on where we are. So we're much more confident in the most recent past, where we have many more analyses, and also the uncertainties in our additional parameters that we need in order to estimate the carbon dioxide are much lower. And so in those times, we might have uncertainties that are sort of on the order of 50 parts per million, for instance. So maybe to give your readers a sense of what we're even talking about, parts per million, we're talking about during the last ice age, we had about 180 to 200 parts per million carbon dioxide in the atmosphere. During past interglacials, warm periods, we had about 280 parts per million. Today, we're sort of at 420 parts per million. So that's been measured with instruments throughout the world, really, and various different locations. The most continuous record is actually on Hawaii, on Mauna Loa. That has been collected since 1958, and we can see every single year of how the carbon dioxide is increasing. So now to go back, the carbon dioxide concentrations, or the uncertainties of these carbon dioxide concentrations over the last couple 100,000 to maybe even 1 to 2 million years are on the order of 50, and then the further back in time we go, plus minus 100 parts per million. And then we go further back in time, and then we're starting to see uncertainties that are on the order of 200, 300 parts per million uncertainty. But then the carbon dioxide concentrations were also on the order of 1,000 to 1,600 parts per million.
Wow.
So that's much higher in the past. And so, yes, we would like to bring down these uncertainties. It's very difficult to do that with these proxies, because we have so many different parameters that are working together in that. But the overall changes are so large that we can be very confident that carbon dioxide was really higher in the past, and it was not just something that was just a minute variation of what we're doing today.
Okay. So to put our current carbon dioxide accumulation in a historical perspective, maybe it was 280 was the typical interglacial level, 280 parts per million, and throughout the last century it's gone up to 430. I think we're at something like that now.
420.
420 parts per million. So we've almost doubled the baseline carbon dioxide level. How odd is this? How far back do we have to go to see levels of that high in the atmosphere from your proxies?
So we have to go back pretty far, and that is something that came out of our study, is that statistically we have to go back about 15 million years in order to see, 14 million years to see carbon dioxide levels that were this high for an extended period of time.
14 million.
And then we can go back even further to see carbon dioxide levels that we might expect throughout the century, by the end of the century. And so that's really quite significant. And what is interesting there is that when we look at the climate, Greenland was not glaciated at that time. So we didn't have any ice on Greenland. Sea level would have been several meters higher than today. So we have about 6-7 meters of ice, ice in Greenland. And Antarctica was not quite as thickly glaciated then as it is now. So it was a quite a different climate at that time. It was much warmer at that time, several degrees, and so it's a different environment that we're talking about.
And that's interesting. Some people will say, "Oh, it goes up and down. It's fine," but 14 million years is a long time. We are experiencing levels of CO2 that have not occurred during the time that humans evolved.
Exactly.
This is the sort of time scales we're talking about to get the levels that we've created in the atmosphere. Now, on the long term, it's probably quite good for flourishing of biological life, because we're all carbon based, and plants, of course, take this carbon and grow with the carbon. But I think what many people don't get in these polarizing debates is the speed, the relative speed of the increases. Over your proxy reconstruction, are there other similar fast transitions that you see in CO2?
So there's one time over these last 66 million years that is probably the closest analog to what we're doing today, and that is the so-called Paleocene-Eocene thermal maximum. So that happened about 56 million years ago.
Mm-hmm.
And it was a time when, due to natural processes, a lot of carbon dioxide was pumped into the atmosphere. And we see that the ocean acidification at the time was similar to what we're expecting by the end of the century. The global warming was similar to what we're expecting, what carbon dioxide might be doing in the future. And the carbon dioxide concentrations were quite high. There was probably on the order, at least over short periods of time, to maybe up to 1,600, 1,700, 1,800 parts per million. So
wow.
These are very high values. What is interesting about that time interval is that it was put into place over a much longer period of time than what we're doing right now. So it probably took about 3,000, 4,000, 5,000 years for that really to happen.
Okay.
When
that's
that
still
happened,
quite fast geologically.
Geologically, that's very, very fast. But what is important about that is that it actually had consequences for marine life, in particular for the plankton organisms that I'm working with. They're mostly not very interesting for most people because who cares about plankton? But these plankton organisms are at the bottom of the food chain. And so if we realize that some of them went extinct or new species evolved, then that means that higher up in the food chain, organisms also would have gone extinct, but we don't have a very good fossil record of them. So we do have lots of evidence for massive dissolution of calcium carbonate deposits at the seafloor. So that's an indicator for high carbon dioxide in the atmosphere and ocean acidification. We see very strong evidence for extinction amongst organisms, excursion taxa that really only lived over the short period of time when it got very warm and the carbon dioxide was very high. And then afterwards, there were new species that evolved. And the most interesting aspect of this is that it took about 150,000 years for Earth to naturally neutralize this carbon dioxide. So that's a very, very long time. And to put that into perspective, the Neanderthals died out about 40,000 years ago. So we're talking about many, many generations of people who will have to live with these high carbon dioxide concentrations unless we manage to, cut emissions soon and reduce emissions, eliminate them altogether, but then also possibly sequester carbon dioxide that has already been emitted from the atmosphere and store it somewhere in a stable reservoir, for instance, in the geological record again, in the form of minerals, for instance.
So getting a little bit into the politics here, I mean, this has become a polarized political issue. I'm sure you hear quite a bit of flack about bias. And I know, you read the posts on social media, and a lot of people are saying that scientists are biased. They're just fudging the data. How do we respond to claims that this is just, you're making up a story? You know what the story should be like, and you're just tweaking the data to align with this story that the CO2 levels have been stable for millions of years, and this is an outlier.
So the carbon dioxide levels have definitely not been stable for millions of years. We know that from various different pieces of evidence from the geological record. So, for instance, we can do our reconstructions, but we can also look at how much calcium carbonate was actually deposited at the seafloor and where was it deposited. And we can see these variations of sometimes it gets deposited to very deep down in the ocean, and then it gets deposited only to shallow depth. And if it's only to shallow depth, then that is an indication that the carbon dioxide levels were much higher, because that carbon dioxide would enter the ocean and would dissolve these calcium carbonate deposits at the seafloor. And so now we have various different lines of evidence that are coming together in order to make these overall estimates and interpretations of our data. We can also see that, we see the temperature reconstructions that go together with our carbon dioxide concentrations. We can look at sea level reconstructions that again show us that the sea level was much higher at the time when the carbon dioxide was higher, when the temperature was higher. So all of this is a pretty strong understanding of our climate system. And these are completely different lines of evidence that are being pulled together in order to come to conclusions. And so the study that we just did was actually specifically trying to figure out, okay, so how bad was it in the past? How high were these concentrations? Because some of these records that we have they were quite scattered. We've had many records that were now decades old. At the time when they were produced, they were the top of the line. They were the best of the best that we could possibly do. But now we have learned a lot more about our proxy systems. And so we've learned how we have to do additional cleaning, for instance, that we have to focus on individual species and cannot mix species. There are lots of pieces of evidence that we have learned over time. And so this consortium that has just worked together here had a real objective look at this and really wanted to, from every single expert group that there is, they looked very closely at these individual records and vetted them and said, these ones are still reliable. These ones are consistent with what we understand about our proxies today. And those are records that we cannot use anymore. And thanks to that, we actually now have a much clearer understanding of what was going on, because many of these records that were very scattered, they have now fallen through the cracks. So they have basically been put on the shelf. Maybe in the future we can measure additional pieces of information to bring them up to our modern proxy understanding. But with the information that we have right now, we cannot do that. Now, in addition to that, the fact that we have time intervals where our carbon dioxide concentrations from different proxies do not match, that tells you already that we're trying to be honest here. Because if we did not want to be honest, we would have sorted out the ones that we don't like and left the ones that we do like. But that's not how we do research. I mean, if we just try to reconstruct what we think we understand, then we're not going to learn anything new. Mm-hmm. And it is important for us to really understand what exactly is happening here, because there may be time intervals in Earth history where there are additional parameters that we have not yet identified, or that maybe we haven't ascribed enough importance to, that might explain some of these changes. And so we really want to understand this in great detail. And for that, we have to live with the uncertainties that we have right now in order to rule out possibilities that maybe the carbon dioxide was much higher or was much lower than we think it was, based on the abundance of data that we have.
Yeah, this is a common issue with describing science or popularizing science, is that, we see science as a gradual approach to a more clear picture, and sometimes we learn new things, like this species gives us different results. We learn things that adjust our previous results and get us closer to the truth, but we don't ever typically throw out old results. We firm them up. We get a finer resolution, a higher precision, or a higher accuracy. Very, very rarely do results get flipped completely on their heads. There are a few very good examples of this change in overall paradigm shift type things, but mostly science is a process of asymptotically approaching a clearer picture, I think. And this is many people don't get that. They know about the paradigm shifts, and they think that all of science is on shaky ground because of the risk of a paradigm shift throwing out everything in the past. And I think the level of work and confidence and understanding that goes into getting these numbers is probably difficult to convey to the general public, I would guess. Like how much work was how many people were working on this project, and how much work did it take to get to these results that you've published?
Well, we had we had a total of 3 workshops over several years that we worked on. There were many more colleagues that actually came to those workshops. In the beginning, we thought we would also work on temperature reconstructions. I'm glad we did not do that, because otherwise we would still be working on that. It's a lot of work. So we probably had over 100 people who have worked on this. In the end, we have 82 co-authors on it who have contributed data, who have helped us document these data. It also took us a long time to document every single piece of information that we need in order to reconstruct carbon dioxide, with every single raw data value that goes into that. So there is, it was a very large consortium of people. That also explains why it took us so long, because we had to find ways of how we can get everybody to agree on this, on how we work on this and how we frame the narrative. We don't want to throw any of these proxies under the bus, because it really is important to us that we get several lines of evidence from different time periods, from different archives. And really only once we have all those lines of evidence, then we can be more confident in our reconstructions. So it was a lot of work to bring this together and to have the conversation between the different groups who in some cases have worked against each other in the past. Somebody comes up with a new reconstruction, and that reconstruction looks slightly different from another one. And they said, yep, ours is right and that one is wrong because of all of these different problems. Mm-hmm. And so we actually have in this study, we also have a very, very long data supplement that explains in detail all the different pieces of information that we have learned about our proxies in the past, and why some of these records have been removed from this compilation right now, what their specific problems are, and so on. So that took a very, very long time to put all this together. But I think it provides a really nice suite of data that can now be used by various different experts to explore these data in even greater detail, and to also put a baseline for the future of how we actually need these data to be documented in order to be useful for future generations. Just because for us, it was sometimes really, really hard to find all the information from studies that were several decades old, or even just a couple of years old. Sometimes it's really hard to find that information when you have to dig through all your lab books and compile it all. But all of those additional pieces of information, they tell us something about how well our fossils were preserved and so on. So it's important information to keep in one place.
Wow. Yeah, that's good. So are you continuing to work on this project in the future, or what's next for the group?
We are. So of course my students and I were actually working on paleo reconstructions to try and fill in some data gaps. So there's some periods of time in that record that have very, very large uncertainties, because over several millions of years we only have 3, 4, 5 data points. So that's not very much, and we're trying to fill that in. But then there are also other time periods where we have some terrestrial records, but not the marine records. So we want to match those up. But then we also have an additional project going on right now that started 2 years ago, and that is now trying to look over the entire Phanerozoic. So the Phanerozoic means the time from the explosion of life 600 million years ago until now.
Very interesting.
We don't have carbon dioxide reconstructions over that entire interval. We have the first reconstructions that have been published. They're probably from 420 million years ago. Many of those records are also very scattered, and so there's a lot of uncertainty in those reconstructions. And so we're working now specifically with a group of collaborators from all over the world again, where we now actually have funding to modernize some of these records. So in the Cenozoic project, we didn't have any money to collect new data and to recalculate or to re-estimate some of these estimates. Yeah. We have done some recalculations, but not collected any new data. In this new project, we now actually have funds to estimate new constraints and then to combine them with the existing ones so that we can actually recalculate all of those data and bring them up to our modern proxy understanding.
Very cool.
So that will take a while. We probably won't be able to do that with all the different records that exist, but at least with some of them. And we're looking forward to providing an even longer record over the next couple of years.
Well, I'll be looking forward to seeing the results of that work come to fruition. Mm-hmm. So thank you so much for joining us and chatting about your work on CO2 reconstructions. Very interesting stuff, and very helpful to put our current situation into contrast with what's gone on before. I think that's I commend you for taking on a polarized topic and doing a good job with it. So thank you so much.
I really appreciate it.
For spending your time. I can send you a Rational View t-shirt if you'd like. I can really appreciate the contributions of the experts that I bring on the show. So thank you so much.
Thank you so much.
If you'd like to follow up with more in-depth discussions, please come find us on Facebook at The Rational View and join our discussion group. If you like what you're hearing, please consider visiting my Patreon page at patron.podbean.com/therationalview. Thanks for listening.